Hello all, and welcome to my final presentation for my project in our DA 5030 class for the fall 2024 semester. My name is Colby Ruggiero, and I'm just going to give you a general walkthrough of the model that I built. And just for a general title, I titled it the National Hockey League Goal Prediction. So just a general run through of the different slide contents that I'm going to go through. I'm going to go through an introduction, just an overview of the project and general data acquisition. Data, I'm going to go through data exploration, then data cleaning and transformation, and then different modeling slides, building the models, and then the performance and tuning, and then the ensemble function, then building it, its performance, and then overall prediction with it. And then I'll just go through a general conclusion. So just starting off, the introduction for this modeling project, we're going to be utilizing play-by-play data for the 2023-2024 NHL season in order to create an algorithm that predicts whether or not a shot on goal did in fact result in the goal. So on the right, just like as the NHL has become more and more statistically advanced, just because of the introduction of uh, new machinery that they're able to use. There's just so much more data readily available to both the teams and the general public on the right. I showed two different examples. One is the NHL Edge platform that the NHL themselves has made available to the public, just tracks all different types of statistics. And then the one on the bottom just shows a general overview of what you might see during a broadcast of an NHL game. And that's just going over various statistics such as skating speed, time on ice, and so on and so forth. And then for our modeling, because these different shooting opportunities are very skewed, we're going to create two different models. So separate. One's going to be normal shots, meaning that they're going to happen during regulation time or overtime, which in our data, which I'll go through before, it's classified as periods 1 through 4. And then one VO shot. So that is technically classified as either a penalty shot or a shootout opportunity or a shootout attempt. So for the data acquisition, the primary way that I went about this is utilizing two different packages, HockeyR and SportyR. SportyR not really for the acquisition, but I'll go through why it's important later. So HockeyR was created by Daniel Morse, who's currently a data scientist for the Seattle Mariners, and the main purpose of HockeyR is to scrape the NHL statistics database that the NHL has, and it allows you to extract the statistics from that page. So it's very useful. And then SportyR is used not just for NHL statistics, but it's used for any specific professional sport that you want, and it allows you to visualize the distributions of whatever statistic you want at hand. So I'll go through that a little bit later with the visualizations, but on the right, on the notebook, you see that HockeyR and SportyR are both installed via DevTools. When running this specific one, I put it in a code chunk that installs DevTools if you don't already have it installed, because you install it through GitHub and then load it. Um, but specifically through the HockeyR package, you want to use the load p by p function on the right that I showed. And then for us, we're doing 2023, 2024. Just note that depending on the connectivity, it usually takes around 30 to 45 seconds for the web scraper to actually enact. I did build in this function end time, just to show at the end of my actual report how long that actually takes. Now moving into the actual data, what we did in terms of encoding, feature derivation, outlier identification, and then splitting and training. On the right on the presentation, I just showed a simple example of some of the feature derivations that we did. So on the right in the actual notebook, just through general EDA, we were able to go through and look at the different types of variables that are loaded in the P by P, and just because there's just such a multitude of variables, I believe it is over 115 variables in just the P by P. We looked at specific variables that we think are going to be useful, where it's event type, event team, event player, goalie, strength, that means 5 on 4, penalty kill, and so on and so forth. The actual X coordinate and the Y coordinate of the player where they are, where this play is happening, shot distance, shot angle, shot type, whether there's an empty net, and so on and so forth. So just being able to gauge through this just EDA, and then this event type is obviously going to be our target variable. And as you can see here, there are so many different ones that we want to go through because there's period start, face off, and those are just completely useless. So we narrowed it down to these five: shot, block shot, miss shot, goal, and failed shot attempt. But according to the NHL, they rank specific shots, or they rank shots generally classified as unblocked shot attempts. So I goals, shots on goal, or missed shots. However, with like the ambiguity that comes with the missed shots, with how to classify it for this specific project, we are going to be only taking into account the event type that is classified as shot and goal. So we're just going to filter the data, go through that. Yeah, so just simple extraction from norm data. Obviously, we said shot type, this is going to be our normal shots data. Shot type, shot or goal, not in fifth period, which equates to shootout, and then not equal to a strength state, 1VO, and empty net equals true. So that's a little bit finicky when you go about that because empty net goals are technically classified as a 1VO and strength state in hockey logs, just for the fact that there is no defender. So this just intricacy you have to take into account. Select all the variables, just rename for general purposing. And then we just also added this because sometimes the goalie isn't necessarily logged in, just to replace it with the actual goalie name with the event type goalie. And then we also did the same thing with PSS data, penalty shot shootout. I'm going to refer to it as PSS for a lot of the time. Just same thing, but then here for the period, we're just going equals to 5 and the strength state equals 0. And then 1VO empty end is false. That's going to be our penalty shots. And then as I say here, just reflecting that. So just with this general transformations and exploration, this is where the Sporty R package comes into effect. So we're able to visualize shots based on like actual rank, and that's where the X fix and Y fix. We're able to see these shot distributions in a different way that histograms, box plots don't necessarily. It's not necessarily going to allow these readers to see like the actual visualization. So at the top, those are specifically slap shots. It's a bit asinine to put all the shots at shot attempts because there's just so many and it would be very difficult to actually distinguish. So these are just slap shots, as you could see the different visualizations. Then on the bottom, since there's fewer attempts, we also see the penalty shot and shootout attempts, as you could see like the different distributions. So now just flipping back a little bit, back to the transformations, including to the encoding derivation. So first and foremost, we are just encoding our goals and shots, or our goals as 1 and our shots as 0. So it's just going to be a binary true false. We're also going to factor it just for our basic classification algorithm. We're also going to do the same thing for empty net, just because it's going to be easier for us to do a little bit of feature engineering. And now we're able to look specifically at the missing values of our data frame. So here we're able to just take a look at the missing values found within our normal shots data. As you can see here, there are 486 goalies that are missing. And that might seem like a little high in our actual data set, but the reasoning behind this is because if there's no goalie and it's empty net goal, it's just going to be not available. So that's a little bit of work through that we have to do, and just say if the goalie's NA but the empty net equals 1, just classify that as no goalie. And then we're also going to filter out after that process is done to just remove any of the rows where goalie is NA. We're also going to do some other feature engineering here on the right. We're gonna encode our shooters and our goalies based on specific ranks throughout the season. So we're also gonna make 3 new variables for each of them. At the point in time for the specific data point that we're looking at for that specific shot, we're going to do the total shots that that player has at that point in the season, the total goals that they have at that point in the season, and then their scoring percentage at that point in the season. We're going to do that for each of the goals, or for each of the shooters, and then for the goalies, we're going to do the amount of shots faced, goals allowed, and save percentage, all up to that specific data point. We're just going to add those to our data frame. And we are also going to encode our shooters and goalies into different groups. So for each shooter and goalie, there are going to be way too many levels if you're talking about it in a factor sense to sort through each level. So say there's 700 different goal scorers or shooters and 90 different goalies. That's going to be way too much maintenance for our classification algorithm. So we're actually going to do rankings for these shooters. We're doing them in groups of four, and we're going to do it based on their scoring percentage and their save percentage, and then we're going to replace the actual name in our data frames with that specific rank. So that's just going to give us a little bit of more leeway. And then we're going to remove unnecessary variables, the team, strength, code, strength, state, x fixed. And then for our norm data, just do that. Then we're going to emit NAs. We're also going to do some outlier identification. So we're going to standardize it based upon z-scores, get the outliers, and we're going to do it for both of these. And we're going to get the outliers counts, the number of outliers for each of them. And since it doesn't affect our levels by too much, we're simply just going to remove the outliers. It removes, we still have quite a bit of shots within these to properly maintain our database. So now we get to move into the actual models that we created. So for our normal shots, we created three different models, and these models are going to be called norm log reg, norm MB, and norm C50. So we did three different ones for each of our data frames. It's going to be logistic regression, naive Bayes, and C50. So for these three different models for the normal shots model we'll start with. First, you got to split into norm and validation. You did it stratified sampling, just so we maintain that or the actual result variable, their actual proportions, split into training and validation. So first, we're just going to normalize the actual the numeric data within these subsets. So just do a standardization of these variables. And then we're going to create one subset where we're going to encode our categorical, or we're going to one-hot encode our categorical variables. And that includes our shooters, our goalies, our shot types, and our strength. So that's going to split those different levels into new dummy binary variables. And then we're also going to make a different subset, and these are going to be factored subsets. So those four different variables that I said before, shooter, goalie, shot type, and strength, instead of one-hot encoding them, these are just going to store them as factors with respective factor levels. Then we could see here for this specific data set, there's a high frequency imbalance between the actual result variables, 0 being just general shot, 1 being a shot that resulted in a goal. So to deal with this, we're going to undersample our majority class. So undersampling allows you to balance the proportions between the result variable. There's also a technique called SMOTE where you oversample the minority class, but in this case, since there are nearly 56,000 shots that are simply that are our dominant majority class, just re-upping this 58,000 with synthetic data would make our data set over 100,000 shots, and that would take way too much computational complexity and time. So we went with the undersampling, and we did undersampling for both the factor data and the encoded data. Norm log reg, we utilized the encoded data just because logistic regression could handle the one-hot encoding far better. K-cross validation did that. Naive Bayes, we used the factor data, and for C50 we also used the factor data. And then on the right here in our presentation, we see after the tuning where for the logistic regression, we ended up removing some of the variables that did not hold significance. Uh, we did the same for naive Bayes and C50. As you can see here, these are the performance of the individual models. You see the logistic regression had the highest accuracy F1 score and recall, and then the C50 had the highest precision. This is after a lot of tuning. At first, a lot of the models were predicting a lot of just the majority class, and that's where we uh, came to the decision to go with the undersampling, where we were able to train our model based upon essentially synthetic proportions. And then now moving into the PSS models, we did the same thing for each of these two on the right. You could see splitting it based upon the 80-20 split, and then normalizing our numeric data and one hot encoding, making that one subset, doing it for both the training and validation. But then we also did this for the factored subsets here as well. And then class imbalance, the frequency is a lot less between the 0 and 1. We still went with the underbalance just because um, it provided our models a much clearer landscape of how they were supposed to go about it. We did it both just with the standard PSS train and PSS validation, but our modeling seemed to work better with the underbalance. So that's what we decided to do. We did encoded again for log reg, and then the factor data for the naive Bayes and the C50. For the sense of showing the actual running of our data, we are going to be able to simply just run through just how our code works. So for this specifically, I wanted to show, I want to start with the actual showing of, so now we could actually run our models to show in real time how it is able to work. So um, starting off with the norm log reg, we're just going to run, but simply because I haven't run anything yet, we're going to run all chunks above. Now we are going to run our logistic regression for our normal data. You'd see here, doesn't take too long to run. Now for naive Bayes, doesn't take too long to run. And then our C50, it takes a little bit long just because the trials are set to specifically 10. And once this is done, we will also go ahead and run our PSS models. The C50 typically takes a little bit of extra time just because of the amount of trials and because of the size of our data set. As we showed before, it was about 56,000 shots and then around 5,000 goals, so just north of 60,000. So now it's completed running. We could also just set our training. And then now we could run our logistic regression for our PSS. So though that in the naive Bayes typically runs a lot faster, and then the C50 doesn't take as long for the penalty shot one, just because they're far less shown in there. Now we can move on to the actual ensemble function, how we built it up. So this is for the normal one and the prediction ref or the actual prediction results, the accuracy, F1 precision, or recall. So for the normal model, it ranked out of, if you're including this in with the three previous models, it ranked 2 out of 4 for accuracy, 2 out of 4 for F1, 2 out of 4 for precision, but then 3 out of 4 for recall. So this is how we built it up. I included a little snippet on the right, but it's a little bit easier if you look at it enlarged on the left. So we just took all the different predictions for the logistic regression, the naive Bayes, and then the C50, combined them, and then sorted them based on their occurrence, and then that's how you return it. So we could run, or we could initialize this function, and then this is how you just run all three. It doesn't take too long, just mainly because you ran everything up. So it's mainly just a sorting function at this point. It takes a little bit longer if you're knitting it and running everything through. So the actual results based upon this, as you see here, it mimics over there. I would say just based upon this, I wish it would favor a little bit more towards as you would go back here towards the norm, more towards the logistic regression model. So I think if we were to go back on this, just to add a little bit more weight towards that logistic regression model, just because of that. Um, then moving back onto the PSS model, we saw that it ranked 3 out of 4, 2 out of 4, 2 out of 4, and 3 out of 4 for accuracy, F1, precision, recall, respectively. I think that's again just resulting to the fact that it's favoring more towards or less against the logistic regression model and more towards the naive Bs and C50, overall just lowering the overall accuracy of the model, which is a bit unfortunate. But as you see here, the on the right, the makeup is very similar, pretty much exact, just with different labels, just the logistic regression, naive Bayes, C50, combining them and then ranking them based on their frequency. Can initialize this function and just allow for these to run again. Just get this same thing. Um, as you can see here, I think the weighting, or not the weighting, the undersampling did help a lot because when we were running it, obviously with normal data with 50 so thousand just shots, not goals, and then only 50,000 goals, it was nearly predicting all to be just simply shots. That took a lot of it. That was a bit unfortunate, but now with the ensemble model, we get a little bit higher accuracy. So just being able to combine these things. So then with our ensemble function, we're able to just create different scenarios. For the normal shot one, we decided that it would be Austin Matthews, the shooter, against Jacob Markstrom, the goalie. And then so far in the season, Austin Matthews has 25 shots. He scored 4 of them so far. Markstrom's faced 95 shots so far, and he saved 90 of them. Shots a snapshot, shot distance of 30, shot angle of 27, even strength. So as you can see here, just adding all these into a data frame. This is going to be the factored data and then making sure that the factors line up and then also encoding it. You see here, for example, snapshot, so encoding it with one. Then we're able to make both those data frames and then we are able to run the prediction here. So going back up here, just making the shot distance. And then with our predicted normal shots ensemble function, include both the encoded and the new factor data because the different models take different data and once again get the prediction of no goals. But then for the penalty shot shootout, we decided to use the same players, but just change up the frequency. Also, Austin Matthews had 7 penalty shot shootout attempts, scored 4 of them. Shot distance and angle will remain the same from the normal shot scenario. Then Markstrom has saved 25, let in or has faced 25, saved 18, snapshot. Just initialize all these as well and then run it through the prediction function, and we get 1. So signifying a goal on this specific equation. So for a general conclusion, just overall the construction of these models is pretty insightful and interesting. Just being able to utilize the hockey R function, be able to scrape through a wide plethora of data, not even the data that I used in these specific models, but uh, throughout the NHL statistics webpage, just how easy it was with this function or with the package and their necessary functions. It was just really interesting being able to dive into this. But in regards to overall model performances, models were really hard to try and tune and regulate just because of the wide discrepancy between uh, the different between the shot and the goal, the disparities between their overall frequency. So trying to tune them. Um, it was just overall like a little bit difficult. But it would be interesting to try and adjust this with different metrics such as like gradient boosting or random forest. I tried random forest a few times, but just the overall computational time and complexity was a lot more difficult to handle with this, and even the even trying like SMOD or undersampling with the random forest or the gradient boosting, it didn't seem to affect the model at all. So just applying different algorithms to this and trying to find the key balance between this, it was kind of difficult, but it's also very interesting at the same time. So I think that even after this project, I'm going to keep on working on this and try and just adapt new ways to see how these different classification algorithms could be applied. Um, Just a little bit of just overall cleanup here. Just with this, I already knitted it, but as you can see here, this is just the overall knitted document. I included a different reference page, and as I said at the beginning of the presentation, here's the total runtime for the load P by P function. I said typically 30 to 45 uh, seconds is how long it takes, and then the total runtime for the overall knitting is going to be around 2 minutes. So that is my overall presentation. And thank you.